Hello. Today we're going to talk about the universal color, and that the universe actually does have a color equivalent to the Planck length. This color is very, very easy to calculate. It's quite simply the Planck length doubled 93 octaves. So it is doubled 93 times. On the screen you will see the equation. The Planck length times 2 to the power of 93, which equals 401.21 nanometers, which is the color violet. I think that's very interesting. It's a good place to start. So, the color of the universe, or this dimension, is actually violet, which is very intriguing because violet is that particular color is very close to the shortest wavelength that the human eye can see. The human eye can see roughly between 380 and 780 nanometers. So it's very close to the highest energy wavelength the human eye can see. Very curious to me, as violet was always seen as one of the most sacred of colors. Moving on, what's even more intriguing is that the phase opposite color of violet calculates to being gold. And on the diagram that you see, you'll see that the Planck length times 1.5 when mapped around the circumference of a circle equals the approximate color of gold. The Planck length being 401.2 nanometers and gold being 601.8 nanometers, approximately. So simply by multiplying the Planck length color by 1.5, you get the value of gold in nanometers. Violet and gold together have always been known as the most sacred colors. However, interestingly enough, this is the mathematical derivative. Just so happens to be those two colors. Gold can also be seen as 3 Planck lengths, for it is the same value. 1 Planck length being its value, violet, 3 Planck lengths being the value of gold. And I'll remind people watching that the values always fall in the octave between the numbers 1 and 2. So they'll always be multiplied or reduced for simplicity to fit between the numbers 1 and 2. So it's a ratio between 1 and 2. For example, 3 Planck lengths is a ratio of 1.5. 1 Planck length is a ratio of 1. Moving to the next slide, there is an example of other derivatives, being the Planck length times 1.25, which gives a value of 501.5 nanometers, or the Planck length times 1.75, which gives you the value of 702.1 nanometers. Also, it can be seen as Planck units. 5 Planck lengths equal 501.5 nanometers, and 7 Planck lengths equal 702.1 nanometers. It can be further explained as Planck length sections. So the Planck length divided by 4 would be 1 plus a quarter for the ratio of 1.25. or 1 3/4, the ratio of 1.75. And so these 4 sections are the fundamental additions of the Planck length, the fundamental modalities extracted by adding Planck lengths together. These derivatives are the first 4, or the first 3, I should say, to show up, not including the Planck length. Gold being the first, ratio of 1.5. Then the aqua color, second, 1.25. And the red color, third, which is 1.75. Moving to the next slide, this is also depicted in a view by stacking the Planck length. So you can see how the octave is arranged, starting from 1 Planck length, then moving to 2, then to 4, then to 8. And you can see how these modalities naturally show up in between the octave simply by stacking single Planck lengths together. The first octave being the Planck length multiplied by 2, the second octave being the Planck length multiplied by 4, and the third octave being the Planck length multiplied by 8. So this is a multiplication table. The Planck length can also be divided. It is in fact the combination of both which allows for all modalities to be extracted. So, moving to the next slide, the more in detail view again of the Planck length, focusing on the 3 firstly derived colors. 1 to 1, 1.25 being 5 Planck lengths, 1.5 being 3 Planck lengths, 1.75 being 7 Planck lengths, and then back to 1. Notice how the numbers are actually reduced to ratios simply by dividing them by 2 until the ratio falls in between the numbers of 1 and 2. 5 divided by 2 until you obtain a ratio of 1.25. 3 divided by 2 to obtain a ratio of 1.5, and 7 divided by 2 to obtain a ratio of 1.75. This chart also depicts counting up from the Planck length, starting from the base. So these are the first 3 derivatives extracted by multiplication of the Planck length and play the most major role in extracting modalities in order to create pyramid shapes. Moving to the next slide, we're going to talk about octaves of angle. So we covered octaves of length. Now we'll cover octaves of angle. The Planck length is 360 degrees in length equivalence. So Planck length being wrapped around the circumference of a circle gives an angle of 360 degrees. And this is the beginning of how to understand how angle is related to length. 360 degrees is not something that you can do much with, but it is the beginning integer of angle division, where it is the whole circumference of a circle. Moving to the next slide, the first division is 180 degrees. It's an octave beneath the primary. So 180 degrees is the first octave beneath the primary or the fundamental angle of the Planck length. Still, not a lot can be done with 180 degrees, for it is an angle not useful for creating pyramids. The next division is 90 degrees. 90 degrees is where it begins in regards to being able to build pyramids on a practical level. The octaves in which pyramids that I focus on and build range between 90 degrees and 45 degrees. It is that range that allows practical pyramids to be built. The 45 degrees representing the Planck length, the 90 degrees representing also the Planck length, being one octave of angle and allowing the entire color spectrum to be covered between those two octaves, 90 and 45 degrees. And once again, a further division of 22.5 degrees. Further divisions aren't used to create pyramids in this work, but are used in the machines for other functions, such as vortex accumulators using angles to draw in energy from copper materials with a much narrower angle. And once again, the final slide depicts the circle divided into these units, 360 degrees, then the octave beneath 180, then 90, then 45, then 22.5, and so on for infinity. However, again, the pyramids that we'll be creating operate only between 45 degrees and 90 degrees, measured from the apex, which will be further covered in future videos. So that's pretty much it. That's the universal color and how octaves of length and octaves of angle can be visualized in the best way that I can explain it.